approximate for x's in between 3 and 6 using 5 left endpoint rectangles. So these are like Riemann sums. Sketch the curve, showing the rectangles used to approximate the area. Use sigma notation to write an expression for the specified area. Determine if the approximation is an underestimate or an overestimate for the actual area. So it's asking us to do several things, and they take some time, but so what we're going to do is make, well, first we're going to sketch the curve. So I recognize that it is a parabola, but I also recognize that I want to draw it in a way that I can actually have a chance at showing my rectangles. So I know I have to go in between 3 and 6, so I scaled my x-axis so that I would have enough room here. And then I started just counting by ones on my y-axis, but then I realized that when I plug in my 3, I get 3 squared is 9 plus 3, I got 12. And then I realized I'm going to have to scale these by, I ended up counting by 5s. So they want 5 left endpoint rectangles. So that means in between 3 and 6, I need to figure out how to divide that up evenly so that I can get 5 rectangles. So what I did is I just went, I wrote 3 over 5. I meant 5 over 3, I think. No, I did mean 3 over 5. So because the distance from 3 to 6 is 3, and I'm dividing it into 5 even rectangles, I went 3 divided by 5 and I got 0.6. So that means I'm going to go, my first rectangle is going to start at 3, and then my next one, this is 3.6. And then my next one is going to be, I just started adding 0.6 each time. So 3.6 plus 0.6 is 4.2. So I just estimated that 4.2 would be right here. And then, what's the next one? 4.8. 4.8, and then 5.4. So 5.4 Okay, so I don't know if you can tell, but I've got myself 1, 2, 3, 4, 5 left endpoint rectangles. And so this 3, when I plug it into the function, its height is 12. This height is 12 right here. And then see how these are touching the, like underneath the curve here? And then so this is 3.6. And so I actually just took 3.6 and squared it and added 3. And that gave me this number here, 15.96. And so on and so forth. You can see this one, this point of my rectangle is touching my curve. If I want to know exactly how high the top of this rectangle is, I can just plug 4.2 into my function. And I'll see that that's 20. Maybe I didn't draw it so perfectly, but that's supposed to be 20.64. And then see, this one's my 4.8. So I tried to draw it so that it looked like it was, the height was 26. See? So basically, these numbers are the height of each rectangle. And I know that the area of a rectangle is base times height. So this little rectangle right here would be, its area is 0.6 times 12. And if I want to, I could just write that number in there. And then I can go 0.6 times 15.96. And then I can go 0.6 times you know, each of these heights. But I found out, I used to do it that way, but I found out that it's way easier to just add up all the heights, find out what that sum is, and then multiply by 0.6. So that's what I'm showing right here. Instead of going 0.6 times 12 plus 0.6 times 15.96 plus 0.6 times 20.64, you know, instead of distributing my 0.6 to each and every term, I'm going to just add these in my calculator, and they ended up being 106.8. Added them up in my calculator, then I multiplied by 0.6. The reason I'm multiplying by 0.6 is because that's this little width for each of the rectangles. This approximates the area under my parabola between 3 and 6. And this is an underestimate. It's an underestimate. Because I could have used the right endpoint rectangles and they would stick out a little bit over the top of the curve. But this one, see, there's gaps, so it's an underestimate. And how on earth did I get, where did I get my X numbers from? Well, I knew that each rectangle has to have a width of 0.6 because I've got between 3 and 6, I got a space of 3 right here, and I had to divide it up evenly into 5 rectangles, so that's where I got the 0.6 from. And so you can just kind of keep adding 0.6 each time. And if I needed to get like a formula or a rule for where these numbers are coming from, I would just go kind of like y equals mx plus b. I was kind of lazy. I didn't want to find the 0th term, so I did it that way where I could just go 3 plus 0.6x. And as long as I start with x is 0, then I can calculate these terms. So what I'm saying here is I wrote this kind of like linear equation here, and I know that if I plug a 0 in first, because what this summation thing does is it takes something plus something plus something plus something. It's a summation. It sums things up by plugging in integers. So if I start with integers between 0 and 4, I plug in 0 to this little formula right here. Well, 0.6 times 0 is 0 plus 3, that gives me my 3. When I plug in 1, then I get 0.6 times 1 plus 3, and that gives me my 3.6. When I plug in 2, I get 0.6 times 2, which is 1.2 plus 3. That's where my 4.2 can come from. So each one of these, I can get those by using this little linear equation. So when I plug this in, because this is where these are my x's. So when I plug this in to my summation, it's going to put x's in here. And the x's that it's going to put in here are going to be these same x's. As long as I start with n, go from n is 0 to n is 4, I'm going to generate 1, 2, 3, 4, 5 terms from this thing. But then to get the y terms, remember we had to square and add 3. So that's why this thing, this is like the x squared plus 3. And I just did it the old-fashioned way, but no matter how you calculate this, you should get 64.08. Now, did we answer all their questions? Determine if it's an underestimate. We think it's an underestimate. I think we're done. That's sigma notation.